NovaTech Automation worked with Penn State Berks to design a Capstone project that would eliminate a labor-intensive process in which they manually straightened aluminum extrusions with an arbor press. Our team worked together to design and develop an automated system to flatten aluminum extrusions within 35 thousandths of an inch. Our design features linear position sensors that accurately measure the extrusion's geometry and an arbor press that applies a straightening load.
Aluminum, due to its lower Young's modulus and high ductility, exhibits a significant springback phenomenon during bending. This means that aluminum has a tendency to return to its original shape after bending. Essentially, the majority of deformation performed is elastic, not plastic. What this means in terms of our project is that if we measured and bent the extrusions to a point at which they were straightened, they would return to a deformed state outside of our tolerance limit. To rectify this problem, we need to bend each aluminum extrusion past perfect flatness to account for the resulting springback. Through comprehensive testing, we have developed an equation to calculate the necessary deformation while accounting for the springback.
To accomplish the needed deformation for each extrusion, our team discussed various methods to apply force into the bend. After a lot of consideration, we concluded that to have a repeatable and controllable process, it was best to use an electronic force input instead of a manual input. A linear actuator offered both an easily controllable and an easily replicated force input by using an Arduino microcontroller.
The next major design decision we made revolved around the layout of the position sensors. The aluminum extrusions are extremely lightweight, and so using 3 or more sensors results in a higher actuation force than the weight of the extrusion can depress. Our design requires the extrusion to lay flat upon a U-channel to accurately measure its deformation. To accomplish this, we placed 2 position sensors near the U-channel walls and calculated their displacement when the extrusion lies flat. We then programmed the actuator to press down on the extrusion until these 2 outer position sensors reached this known displacement.
With the weight issue now solved, we discussed how to measure the extrusion's deformation. When doing research into the orientation of the bends, we found that all of the extrusions bend in the same vertical orientation, usually in the center. With this knowledge, we decided to align 3 position sensors vertically in the middle of the U-channel so that we can average the displacement read by each sensor. Averaging 3 sensor values allows us to get a more accurate representation of the bend present in the extrusion, as more data points yield higher precision. The one downside to the sensor placement is that it becomes impossible to accurately measure bends in the extrusion if they're not in the center. To eliminate this weakness, we added slots in the U-channel, allowing it to be manually moved under the arbor press ram, thus ensuring that the bends are always centered. These slots are conveniently designed with margins large enough to accommodate a standard wrench, allowing for effortless adjustments.
Safety was a chief concern and held high significance throughout the design process. Industry standards were consulted and elements were integrated to ensure operators were well removed from the bending process. Using 2 latching switches ensures the operator's hands are removed from moving parts of the press and the actuator, reducing the risk of pinching, pressing, and injury. In addition, an emergency stop is integrated and easily accessible, discontinuing all operations when engaged. The automated nature of the operation reduces human interaction, further reducing the risk of injury. From risk assessments to redesigns, our team was driven to protect users and prioritize safety.
After considering everything we have covered, here's how our system functions. The user places the warped extrusion under the arbor press, then presses 2 buttons, allowing the process to commence. Linear position sensors measure the extrusion to determine the initial bend. An actuator is used to achieve the desired deformation, pushing the arbor press handle and moving the ram downwards to the appropriate depth. This is all calculated by the microcontroller. The linear position sensors continuously measure the bend during this process, which creates a constant feedback loop on the arbor press ram's position. Once the operation is completed, the linear position sensors remeasure the extrusion to determine if the required flatness has been achieved, and this is all then displayed to the user through LEDs on the control panel.
Throughout the entire design process, we ensure that every component of the system can be disassembled easily from the arbor press with standard shop tools. By designing the system in this manner, we ensured that the normal functionality of the arbor press was maintained. We want to thank Josh Wetzel and NovaTech Automation for sponsoring this Capstone project. Another big thanks to Dr. Nathan and the entire engineering department at Penn State Berks for their help and guidance in making this project a success.